Welcome in video 12 on fair valuation. This is the last video on the fair valuation presentation. We will see some general exercises here in with applications in two-step valuations, and then we will also make some general conclusions about fair valuations. Let us first have a look at exercise 21. And exercise 21, the setting of exercise 21 was also considered in exercise 13 for hedge-based valuations. Here we will have the same setting as in exercise 31, but it will be in a setting of two-step valuations. So we consider again a financial actuarial world where the universe is given by four couples which present the states of the world or the scenarios in which we are interested at the end of the year. The four couples are 0, 0, 0, 1, 1, 0, and 1, 1, where the first component of each couple denotes the price Y1 of stock 1 at time 1. So this price can only be 0 or 1. And the second component is the value of the survival index I at time 1, and the survival index can be equal to 0 or 1. There are physical probabilities given. P00 is 1 over 6, and so on. So these are the probabilities under the physical measure P. Notice that all these probabilities are positive, larger than 0. Then, in this financial actuarial world, there is two traded assets, a traded zero coupon bond and a traded stock. The current price of the zero coupon bond is 1, and its price at time 1 is also equal to 1. So the risk-free interest rate is 0. There is also a traded stock with current price 1 over 2 and with price at time 1, Y1, which is 0 or 1. Then there is another claim in which we are interested, but for the moment it is not traded, is the survival index. The survival index, I can take the values 0 or 1 at time 1, and it will be 0 in case few people survive. It will be 1 in case many people of a given population survive. There is another claim in which we are interested, a non-traded claim, S, which is the product of 1 minus I and 1 minus Y1. Notice that we know from exercise 13 that in this setting, the claim I, or the non-traded survival index, is an orthogonal claim. And of course, Y1 is traded and hence is a hedgeable claim. Now, the first thing that we have to prove is we have to show that any derivative of Y is in fact any function of the two traded assets, or function of the two traded time 1 asset prices, Y0 and Y1, is hedgeable. So our market is complete in the sense that any derivative of Y here is hedgeable. Let us prove this. So we have that Fy is in fact f of 1 y1, because the zero coupon bond will have value 1 at time 1 and the stock will have y1 at time 1. This f1 y1 can only take two values depending on the value of the stock. If the value of the stock is 0, it will be f1 0. If the value of the stock is 1 at time 1, it will be f1 1. Now we will look for a hedge for this Fy. Let us call the hedge, denote the hedge by mu. So if mu is the hedge, then the time 1 value of this hedge, mu times y, mu multiplied by y, must be equal to Fy. Or we can write mu 0 multiplied by 1 plus mu 1 multiplied by y1 is Fy. This equation, we have a look at this equation for the different possible outcomes of the random component y1. So y1 can be 0 and 1. If y1 is 0, we have this expression. For this relation transforms in this. If y1 is 1, we have this expression. So we can solve this for the two unknowns, u0 and u1. And u0 is given by f10, while u1 is given by f11 minus f10. So that means that the derivative Fy can be written as the time 1 value of the hedge u with nu0 f10 and u1 f11 minus f10. So we have proven indeed that any derivative of y is hedgeable. So our market is complete in omega fy, where fy is the sigma algebra generated by the vector y. Now let us consider the fair conditional valuation pi y with underlying actuarial valuation pi. So we say it's a fair conditional valuation, we do not specify it, it's a general fair conditional valuation. And there is the non-traded claim S also. Then let us now have a look at the second question. We have to express the two-step hedge theta two-step S of pi y of S and the two-step value rho S is expectation under Q of pi y of S as functions of pi 1 minus I. Well, our market is complete in the sense that any derivative is hedgeable, and then we have seen in this case there exists a two-step hedge. Any claim can be hedged, any derivative can be hedged. So in particular, pi y S, which is a derivative, the conditional valuation transforms S in a derivative. This derivative must also be hedgeable, and the underlying hedge we denote that by theta two-step S. Let us try to derive this two-step hedge. The two-step hedge, theta two-step S of pi y of S, follows from the following expression. The time one value of the two-step hedge of S must be equal to pi y of S. Or we write this vector product as a sum of 2 0s multiplied by 1 plus 2 1s multiplied by y1. This must be equal to pi y of S. S is 1 minus I multiplied by 1 minus I y1. Now, let us have a look at the different cases, y1 0 and y1 1. This expression transforms in the first expression in case y1 is 0. It transforms in the second equation when y1 is 1. So if we have a look more closely, we find that theta 0 of S must be equal to pi of 1 minus I, and theta 1 of S must be minus pi of 1 minus I, where pi, of course, is the underlying actuarial valuation of the conditional valuation pi y of S. So we have found that the two-step hedge of S, the two-step hedge of S is given by pi 1 minus I. That's the number of zero coupon bonds that we have to buy, and minus pi 1 minus I. So we have to sell pi 1 minus I stocks. Okay. Then further, now we have that pi y of S, that's the conditional valuation of S, is equal to the time one value of the hedge, the two-step hedge of S. This two-step hedge is equal to pi 1 minus I minus pi of 1 minus I. We multiply this by the time one vector, 1 y1, and we find that this is equal to pi multiplied by pi of 1 minus I times 1 minus y1. So we have expressed the conditional value of S as a function of pi of 1 minus I. Let us now have a look at rho of S, where rho of S is the expectation under Q of pi y of S. So we have the expectation under Q of pi of 1 minus I multiplied by 1 minus y1. And if we work this out a little bit, we find that this is 1 over 2 pi of 1 minus I. So the value, the two-step value of S in our particular setting is 1 over 2 pi of 1 minus I. Important remark, we do not have to choose Q because any Fy is hedgeable. Hence, also pi y of S is hedgeable, and rho S is the price of that hedge, and this price is uniquely determined. So our rho of S does not depend on the particular choice of Q. Then there is a third question. In the third question, one asks to determine the two-step cost of capital value, ρS of S, when the cost of capital is 6% and when the probability level is 99.5. So, question 3, we start from the two-step cost of capital valuation. So rho of S is then given by e to the power minus r expectation under Q of the conditional expectation of S given I under P plus I times the value at risk at level P of S given Y minus the expectation under P of S given Y, and the underlying actuarial valuation for the two-step cost of capital valuation is in fact the cost of capital principle, pi of x, given by this expression. So let us now find rho of S. Rho of S is rho of 1 minus I multiplied by 1 minus y1. Because of question 2, we know that this value is equal to 1 over 2 pi of 1 minus I, and the pi is this underlying actuarial valuation. So if we take this value for 1 minus I, if we take this expression for 1 minus I, we find that rho of S is 1 over 2 multiplied by this whole expression here. What we still now have to do is we have to find the expectation under P of 1 minus I and also the value at risk under P, the value at risk under the measure P, the value at risk at the level 99.5% of 1 minus I. Well, 1 minus I can be equal to 0 or 1 with probabilities 1 over 2 and 1 over 2. Therefore, we know already that the expectation of 1 minus I is 1 over 2. And then the value at risk at level 99.5 of 1 minus U. If you look at the distribution, the cumulative distribution of 1 minus I, we take the 99.5 level, so the value at risk is 1. If we introduce all what we found here and here in this expression, we find finally that the value of S, rho of S, the two-step cost of capital value of S, is 53 divided by 200. Let us now continue in exercise 21.2, but we add an additional traded asset in the financial market. So we are in the same setting as in exercise 21.1, but apart from the zero coupon bond and the stock, there is also a survival index. The survival index is also traded. The payoff Y2 is equal to I, and the current price Y2 is equal to 2 over 3. The claim S, as we defined before, is still non-traded. So now we have a market with 3 traded assets. And then we have a first question. Show that Q is Q00, Q01, Q00, Q10, Q01, Q11 is an equivalent martingale measure for the financial market in our probability space, if and only if the following holds. Q00 is an element somewhere in the open interval 0, 1 over 3, and then Q10, Q01, Q11 follow from the explicit value for Q00. That's the first thing that we have to find. So Q is an equivalent martingale measure, we know already, if and only if all the Q's are strictly positive, because the equivalence condition is the condition that in fact all Q's are positive, because all P's are also positive, and moreover there are the 3 martingale conditions. Expectation under Q Y0 is 1 and these 2 others. So Q is an equivalent martingale measure if and only if these 4 Q's are positive and have to satisfy this set of 3 equations which follow from this set here. Or if we work this out a little bit, we find that Q is an equivalent martingale measure if and only if all the Q's are strictly positive and the marginals are fixed. Q0 dot is 1 over 2, Q1 dot is 1 over 2, Q dot 0 is 1 over 3, and Q dot 1 is 2 over 3. So there are many solutions. There is more than one solution possible. Well, the reason that there is more than one solution possible is that, in fact, here we see that we have to look for 4 Qs, but there are only 3 conditions. So in order to work this further out, let us just have a look at all Qs which are strictly positive, such that Q00 is Q, let's say, let's call it Q, and once we know Q, we know all the other values, all the other probabilities, Q01, Q10, and Q11 are functions of Q. So now we have to ensure that all our Qs are strictly positive. So that means that here the Q has to be strictly positive, 1 over 2 minus Q has to be strictly positive, 1 over 3 minus Q has to be strictly positive, and finally 1 over 3 plus Q has to be strictly positive. So that means that in fact Q is an equivalent martingale measure if and only if the Q here must be an element in the interval 0, 1 over 3 in the open interval. Q00 is then equal to Q, Q01 is 1 over 2 minus Q, Q10 is 1 over 3 minus Q, and Q11 is 1 over 3 plus Q. With this, we have indeed proven that there are an infinite number of Qs possible, equivalent martingale measures possible, so the market is incomplete in omega 2 to the power omega p. Now, let us show that the claim S is 1 minus I multiplied by 1 minus y1 is a non-hedgeable derivative of y. It's a derivative of y, that's obvious, because it is a function of I and y1, and I is equal to y2. So it's a function of the traded assets, but it is non-hedgeable. Let us try to prove that. Well, we find here S is equal to 1 minus I multiplied by 1 minus y1 is equal to Fy. That means that S is a derivative, but let us now also have a look at the expectation under Q of S. The expectation under Q of S is the expectation under Q of 1 minus I multiplied by 1 minus y1. And this is Q00. And Q00 can be an element in the interval 0, 1 over 3. So S cannot be a hedgeable claim. S is not hedgeable because the expectation under Q of S depends on Q. In case S was hedgeable, then it could only have one price. And now we have seen that there is an infinite number of prices possible for S. So that means that indeed S cannot be hedgeable. Question 3. Question 3, we have to show now that the two-step cost of capital value rho S of S is given by rho S is Q00. From the Brennan-Schwarz formula for two-step valuations, we know already that rho of Fy is e to the power minus r expectation under Q of Fy, provided by y of Fy is e to the power minus r Fy. This is a special case of the Brennan-Schwarz formula with an orthogonal claim as orthogonal equal to 1. Now, this result, this condition here, holds for two-step cost of capital valuations if Fy is larger than or equal to 0. We have seen that for two-step cost of capital valuations, this condition holds, so that means that this formula must hold. Hence, rho of 1 minus I multiplied by 1 minus y1 must be equal to the expectation under Q of 1 minus I multiplied by 1 minus y1, and this is Q00, which is an element of 0, 1 over 3, and depends on the choice of the equivalent martingale measure. So we have proven question 3. Now, finally, question 4. Determine the two-step cost of capital value of S in case I and y1 are independent under Q. So, even if there is independence between I and y1, between the index, the survival index and the stock, that doesn't mean that there is independence under Q, but let us now assume that there is independence under Q. What is in this case the two-step cost of capital value of S. Okay, we know already that Q is an equivalent martingale measure if and only if the marginal distributions for the stock Q0 dot and Q1 dot are given, and the marginal probabilities for the survival index Q.0 and Q.1 are also given by these values. So we see that only the cumulative distribution functions of Y1 and I are fixed, and there is not any dependency structure assumed or condition, not any condition on the dependency structure. Now let Q orthogonal be the equivalent martingale measure where Y1 and I are Q independent. So the margins are fixed, but let us now assume independence between Y1 and I. Then Q00 under this orthogonal Q is Q0 dot orthogonal multiplied by Q.0 orthogonal. These two marginal probabilities, we know them, they are 1/2 and 1/3. So Q00 orthogonal is 1/6, which means that the two-step value rho S of S is given by Q00 orthogonal is 1/6. So we have indeed determined here the two-step cost of capital value of S in case I and Y1 are independent under Q. Now we go to a further step in the exercise 21. We have the same setting, again the same financial actuarial world as before with strictly positive probabilities, but we add, apart from the zero coupon bond, the stock and the survival index, we add a fourth traded asset, an exotic call option. The current price of this call option is 1/6. Its payoff at time 1 depends on the survival index and depends on the performance of the stock market. It is Y3 is equal to I times Y1 minus 0.5 plus. So it is 1 in case many people survive and the stock market goes down, and it is 0 in any other cases. And then there is a non-traded claim S again, which we want to value in this extended market. The first exercise that we have to answer then, question that we have to answer is then, show now that our market has become complete in omega 2 to the power omega p. We can expect that it is complete now because the marginals, the index and the stock are traded, and also the dependency structure is traded via this exotic option. Well, let us prove it a little bit more formally. We know that Q is an equivalent martingale measure if and only if there are strictly positive Qs that satisfy the 4 martingale conditions. The first 3 martingale conditions plus the strictly positive conditions translates in this 1, 2, 3, 4 conditions for some Q in 0, 1/3. And there is a third, an extra condition now, expectation under Q of Y3 is 1. And this condition, this fourth condition translates in Q11 multiplied by 1/2 is 1/6. If we work this out, we find that Q00 is 1/6, Q10 is 1/6, Q01 is 1/3, and Q11 is also 1/3. So there is exactly 1 equivalent martingale measure left. So that means that our market is indeed complete as we had to prove. The second question then, let us determine the hedge now of S is 1 minus I multiplied by 1 minus Y1. S is hedgeable because our market is complete, so let us look for its hedge. The hedge, let us denote the hedge by nu. The time 1 value of the hedge, nu multiplied by Y, must be equal to S or 1 minus I multiplied by 1 minus Y1. We can rewrite this condition in this way here. And now let us have a look at this condition for all possible scenarios, 0, 0, 0, 1, 1, 0, and 1, 1. These are the 4 conditions that we find. And if we work this out, we find that U0 is 1, U1 is minus 1, U2 is -1, U3 is 2. Hence, the hedge for the claim S here is the nu times Y, is nu, sorry, with nu 1, -1, -1, 2. So we found the hedge S, and now show now that any fair value of S is given by rho S is 1/6. Well, anything is hedgeable, so also S is hedgeable. So the fair value of S can just be the financial market value of S, which is unique and must be 1/6. The proof is given here. For any hedgeable claim, we have that rho SH is e to the power minus our expectation under Q of SH. So let us try to calculate this rho for the claim S, which is also hedgeable, and we find that this must be equal to 1/6 indeed. This was exercise 21. Let us now have a look at exercise 22, which is also similar to exercise 14 that we have seen in a hedge-based valuation context, but now this is the same setting in a two-step valuation context. We consider, as before, a national population of n not members, where I is a Bernoulli variable which can only take the values 0 or 1. 0 if member I dies before time 1, 1 in the other case, hence if he survives. There is a national survival index, I, which counts the number of survivals, so all the ones of the corresponding Bernoulli variables. Now there is also an insured population of n insured members, and for each of these insured, we define also a Bernoulli variable gi, which can be 0 or 1, whether the insured I dies or survives. And now we immediately assume, the insurance claim now S is then G1 plus G2 plus Gn insured, so the insurer will pay 1 to any surviving person in its insured population. Now we make an assumption that n insured is smaller than or equal to n national, and Gi corresponds or is identical to II for I is 1 to n insured. This means in fact nothing else than that the insured population is a subpopulation of the national population. So the national population and the national index is, for instance, in Belgium situated. The insured population, all the insureds are Belgians. And they take part in this index. They are also part of this national index. Now there is a financial market consisting of a zero coupon bond with current price 1 and price at time 1 e to the power r. There is a stock with current price y1 and the price at time 1 is the random variable y1, which takes values in a set A, let's say. And there is the national survival index, which current price y2 and the price of at time 1 y2, or the payoff at time 1 is I. So the national survival index is traded, and at time 1 you receive the number, an amount equal to the number of survivors in the population. Then the financial actuarial world is described by omega to the power omega p, where omega is the set of all scenarios in which we interested, is x1, x2, x3, where x1 is an outcome of the stock, x2 is an outcome of the national population, and x3 is an outcome of the number of insureds. Okay, then hence omega is a support, of course, of y1 is. We assume now also that y1 and is are p independent, so that means that the evolution of the stock and the evolution of survival is independent under the measure p. And we suppose that the fair value of the insurance claim S of the number of survivors in the insured population is determined by the two-step standard deviation principle. So rho S is determined as e to the power minus r expectation under Q of, and then in the inner step we take a conditional standard deviation principle. Conditional expectation of S given Y plus alpha times the conditional standard deviation of S given Y. First thing to prove is show now that in this case the two-step standard deviation value rho S is given by this expression. So rho S divided by the number of insureds, or let's say the premium per insured, is equal to Y2 over N divided by N national plus an additional term, and this additional term looks similar but is different from the one that we have seen in the exercise on the hedge-based valuation. But we see in any case, if the number of insureds increases, this additional term decreases, and in the theoretical case that the number of insureds is equal to the number of the national population, so that means everybody in the national population is insured, then this second term just disappears. This is normal, because in this case that insured and national are equal, then in fact the insurance claims are traded. That's just the outcome of the survival index. And then you just buy the survival index as a hedge. Now we make some additional assumptions. A is a countable set, and all I are independent identically distributed under P with the probability that II is 1 is P. But before we make these additional assumptions, let us first try to solve question 1. Question 1 goes as follows. We know that, let's start here, rho of S is given by this value. We need to know a conditional expectation of S, conditional on Y, and a conditional standard deviation of S given Y. Y here is this time 1 vector of asset prices is e to the power R, Y1 and I, and we also know that S is orthogonal of Y1. We assumed that survival and the stock market's evolution are independent. So that means that these conditional expectations of S on Y here and here can be replaced by conditioning just on the index value because of the independence between S and Y1. And then you can prove that this is equal to, now we need to have an expression for expectation of S given Y and the standard deviation of S given Y. Well, these expressions are given and can be derived. They are shown here. Expectation of S given Y is equal to this expression, and the variance of S given Y is given by this expression in a general case. So, but we just take this expressions as given, and then we get here, if we fill this in these expressions from the slide a little bit further, we find finally that rho S divided by the number of insureds, or the premium to be paid per insured, is indeed equal to this expression. Okay. So this is our general setting, so we did not assume that the IIs or the survival of the individual persons, that they have to be identical or that they have to be identically distributed or independent. We did not assume that. It's a little bit, the additional term, the risk margin, let's say, is a little bit a weird term because it's an expectation under Q of Y2, and here also Y2, so of Y2 squared. We will have a look at it in a special case. We will assume that A is a countable set, and we will assume that all II are independent, identically distributed with probability of survival equal to P. In this case, the question now is to write down the set of equations which determines the set of equivalent martingale measures for the financial market. Let's have a look at question 2. So Q is an equivalent martingale measure if and only if Q is equivalent to P and Q satisfies these 3 martingale conditions. So we can rewrite this as Q is equivalent to P. The first equation is the martingale condition for the zero coupon bond, transforms in this. The second equation is the martingale condition for the stock, And the third equation is the martingale condition for the traded index. Okay. Let us now have a look at the next question, question 3. The question is now, does rho s depend on the choice of Q? So our rho s is defined, is given here. It's an expectation under Q of a term that contains y2 and also y2 squared. So the question is, does the choice of Q gives another value for rho of s? That's the question. Well, as we have just observed, rho s can be written as something plus the expectation under Q of the square root of a times I plus b times I squared for some fixed deterministic a and b. So in fact, it's an expectation of the square root of a function of I, the traded survival index, and I squared. Now, it is obvious that this square root a times I plus b times I squared is not hedgeable. You cannot find a linear combination of the traded assets that gives as outcome that has time 1 value equal to the square root a times I plus b times I squared. So rho s definitely depends on the choice of s. Then let us now suppose that Q is an equivalent martingale measure under which all II are independent identically distributed. So we make an assumption that under the measure Q, the IIs, the Bernoulli variables denoting survival or not, are independent identically distributed. In this case, you can determine the Q distributions of I, and S respectively. This is performed in exercise in question 4. So if we suppose that all II are independent identically distributed under Q, then e to the power minus r expectation under Q y2 is y2 can be written in another way. We can just sum over all I expectation under Q of yy is e to the power r y2. Now the expectations under Q of yi are equal because they are all identically distributed, the II. So the expectation under Q of ii is e to the power r multiplied by y2 divided by n national. So we find that Q, the probability that ii is 1 under the measure Q, is given by this expression. Remark, we do not need the Q independence assumption here. Identical distributions under Q are sufficient for the IIs. What is now the distribution of y2? Y2 is under Q a sum of Bernoulli variables, and the number of Bernoulli variables is n national. So this is a binomial distribution with the number of trials, let's say n national, and the probability of success of a trial is Q ii is 1. So the probability under the measure Q that y2 is x2 is given by this expression of the binomial distribution. Here, of course, the Q independence between the different IIs is essential. And in the same way, we know that S is also binomial distributed. The insurance claims, the number of insureds who survive is also binomial distributed with number of trials n insured, and the probability that an outcome is 1 is Q ii is 1. So we can find an expression for Q S is S from the general expression for the binomial distribution. Then we have question 5. Now, is rho S uniquely determined in this case? So if we assume that all II are independent identically distributed under Q, is now rho S here uniquely determined? The answer will be yes. The reason for that is given here. Because the cumulative distribution of y2 is fixed. So the cumulative distribution of the traded index is fixed, is known. So that means that but it does not mean that Q is uniquely determined. For instance, the Q distribution of Y1 is not fixed yet. But let us have a look at this expression. So if we know the distribution of Y2, so here we have just an expectation under Q of a function of Y2. And the distribution of Y2 is fixed, so the expectation under Q of this term is indeed fixed. So rho S is uniquely determined in this case. Let us then have a look at exercise 23. Exercise 23 is about comparing hedge-based valuations and two-step valuations. If I suggest you to have a look at exercise 23 once you have studied all the material before, and if you can solve exercise 23 on your own, especially the questions 1, 2, 3, and also 4, 1, 2, 3, and 4, if you can solve these questions, then you're ready, you're well prepared for the exam. I will not have a look in detail at the solutions of this exercise. You can find them in the solutions to the exercises, but let us just go a little bit through the exercise to see what are the questions that are relevant here. So we have a non-negative alpha. We consider a valuation rho, which is defined in the following way. Rho S is the time zero value of the hedge of S plus alpha times e to the power minus r expectation under Q of sigma p of S given Y. So this rho of S is a little bit strange. It is a combination of a hedge-based valuation, because we have the time zero value of the mean variance set of S, but the second term looks a little bit more like the two-step valuation. So it's a combination of the hedge-based valuation and a two-step valuation. A first question that is then asked, show that rho is a fair valuation. In order to show that rho is a fair valuation, you have to prove first that it's a valuation, hence that it is normalized and translation invariant, and then you have to prove that it is model consistent and market consistent. Again, make this exercise, this question, try to answer it by yourself. If you have doubts, just have a look at the solutions. They are described in detail here. The second question then is now, once that we know that rho is a fair valuation, we have seen that any fair valuation is a mean variance hedge-based valuation. So question 2 is about, okay, if this is a fair valuation, express this rho as a fair valuation. Show that rho can be expressed as a mean variance hedge-based valuation. And in order to help you a little bit, I give you already the model consistent valuation below. The model consistent valuation related to this mean variance hedge-based valuation is given by this expression. The solution, try to solve it by yourself. The solution, you can find it also in the solutions manual. Third question now, this rho is fair, hence it also must be a two-step valuation. So, question is, try to express this rho as a two-step valuation, and what is the underlying fair conditional valuation, pi y? In order to help you a little bit to solve this question, this is given here already. So the pi y of S, the fair conditional valuation, pi y, is given by this expression. Fourth question then is, let us now assume that SH is non-negative and S orthogonal is an orthogonal claim. Let us now calculate for this general valuation that we defined on the previous slide. Let us calculate rho of SH multiplied by S orthogonal, or better, let us try to show that rho of SH multiplied by rho that rho of SH multiplied by S orthogonal is equal to rho to step of SH multiplied by S orthogonal. And what is rho to step? Rho to step is the two-step standard deviation valuation with parameter alpha. Try to prove this, that in fact for unit-linked related claims as H multiplied by S orthogonal, in fact, the row that we defined corresponds with the two-step standard deviation valuation. And then, if you can solve, like I said, if you can solve this first 4 questions by yourself, then you're ready for the exam. You're well prepared for the exam. Here are some more difficult, more subtle questions, which are less important for an examination, but to check whether you know the theory very well or not. Question 5 is a question about, does the following statement hold? So we have seen that the row and the row two-step, they coincide for this kind of product claims as H multiplied by S orthogonal. The question is this equivalence, is this equality also holding for any claim? So is the row that we defined on the previous slide, is that the same as the two-step standard deviation valuation that the two-step standard deviation valuation for any S? The answer will be no. But question says then, 6 then asks, does this statement above, so this equality holds in case all derivatives of Y are hedgeable? So if our market is complete in the sense that all derivatives of Y are hedgeable, in that case, do we then have that rho corresponds with the two-step standard deviation valuation? As I just mentioned to you, the answers to all these questions are also here. So this is almost the end of the set of presentations on fair valuation. Let us conclude, or let us have a look at what we did. We introduced the fair valuation of financial actuarial liabilities in a very simple setting, namely a single period setting. What did we do? We combined prices observed in the financial market with a valuation based on an actuarial model. So that means that we used both P and Q measures. Both were involved to set a good fair value. And then we have proven that there are a number of statements equivalent. Saying that rho is a fair valuation is in fact saying the same as rho of S is equal to the X discounted is the time zero value of a fair hedge of S. So any fair valuation is in fact nothing else than the time zero, or gives as value rho S to any claim S, the time zero value of a fair hedge of S. Rho is a fair valuation is also equivalent with saying that rho is a hedge-based valuation, and rho is a fair valuation is also equivalent with saying that rho is a two-step valuation. So all these statements are all equivalent. Important to notice is that we have defined an actuarial valuation in a very specific way. An actuarial valuation was a best estimate plus a risk margin, where the risk margin is P-law invariant. But all the equivalences here, these 4 equivalences here, remain to hold for any subjective choice of the properties that an actuarial valuation has to satisfy. So it's not just restricted to our choice of the definition of an actuarial valuation. Then, in fact, all the things that we have discussed in this fair valuation presentation come from this paper here, which is in fact a static valuation of time t claims, and we consider static hedging. What does it mean? A static valuation is a time zero valuation. We only value at time zero. A time t claim, time t, well, we always considered a time 1, but we could as well have considered time t, provided we have a static hedging environment. Static hedging means that we set up the portfolio at time 0 and we keep the portfolio until the end of the period, time t. So this is what we consider. We can generalize these results in very many ways. One is we could also have a look at the static valuation of time t claims in a dynamic hedging area. So what does that mean? We have a time t claim, a claim to be paid at time 10. We do a static valuation, so we want to value it at time 0 now, but we allow dynamic hedging. There is 10 years to go, and we are allowed to change the portfolio from time to time. For instance, we are allowed to yearly change the portfolio, adapt the portfolio. This is not considered in this presentation, but you can find all the details about that in the paper by Gu and Dana of 2019. And an even more general setting is we have time T claims. We allow dynamic hedging, so the portfolio can be rebalanced, the investment portfolio can be rebalanced, but it's a dynamic valuation. So that means we do not only value at time 0, but we also value at time 1, time 2, time 3, and all these valuations in one way or another have to be connected. But again, to summarize, the things that the model that we considered here was a static valuation, a time 0 valuation of a time T claim with a static hedging approach. So we only set up our investment portfolio at time 0 and we do not change the portfolio anymore. Then there is an appendix. We have seen that any fair valuation is a hedge-based valuation and is a two-step valuation. So here we show how a fair valuation can be expressed as a hedge-based valuation and how a fair valuation can be expressed as a two-step valuation. And also starting from the hedge-based valuation, here we show how you can transform this hedge-based valuation into a fair valuation here and a two-step valuation. And finally, we also look at, starting from the two-step valuation, how do we transform it in a fair valuation and a hedge-based valuation. Okay, that's the end of the presentation on fair valuation.